Hi guys, today I would like to discuss a new concept, force on a moving charge in a magnetic field. Let us try to understand the statement. If a charge is moving, that is in a magnetic field, not in electric field, it's in magnetic field. So on the charge some force is exerting, and we know that in electric field, suppose it is positive plate and if it is a negative plate, if I release an electron, so this electrons is try to attract towards to positive plate. This knowledge we know it because charges attract each other. Likely if you release a positive charge, so that attracts towards to negative plate. So here we understand the path or the curvature. It won't go straight, it will move. That is due to attraction. That's due to because of electric field. But here, if a charge is moving in a magnetic field, so on the charge some force is acting. So what you are seeing is a very powerful picture. These are the tracks, moving tracks of an electron and a proton in a uniform magnetic field. This is photographed at Lawrence Berkeley Laboratory. So you can see the spiral tracks of electron and proton. They are both moving in oppositely, but you can see the spiral tracks. So what could be the reason here? The formation of track set here. That is due to because of some force. And you know it here, by studying these tracks carefully, they estimated the mass of electron and mass of proton. So a charges are two types, electron and proton. When they both move in magnetic field, so there is a certain pattern of their movement that happens in magnetic field. If we can analyze these tracks, that study known as mass spectroscopy. So by studying that, we can able to find the mass of any kind of molecules. That is entirely different concept. So here this diagram shows evidence that there is certain force which acts on the charge. Let us try to visualize that. Here horseshoe magnets, you can see the magnetic field on them. The magnetic field on them towards north to south pole. And here one positive charge is ready to move between the magnetic field. So the direction of the positive charge is perpendicular to the magnetic field. And because of the presence of the charge in the magnetic field, that causes a force. Here you notice a downward force from the north to south and an upward force from the another side. Suppose if you can release a positive charge, here you can see the movement of positive charge. It do not move straight. So let me play again. You notice that carefully in the magnetic field. So due to because of the force which is acting downward direction, the charge is moved downward, and again the charge moved upward direction. Now here The three arrow marks are the three vectors. The charge is moving with a velocity. The green arrow marks represents the velocity vector, and the silver arrow mark is representing the direction of magnetic field. It's also a vector. So because of the interaction of the velocity vector of moving charge with the magnetic field vector, so the resultant causes a force. That force caused the positron move down at there. It is moving down, and at other side it is moving up. Why it is moving up? Here one and only thing has changed, that is magnetic field direction has changed. The velocity of the positron do not change, but magnetic field direction has changed. So due to the interaction of the velocity of the charged particle with the direction of the magnetic field, that causes a force. That force here clearly visualized the movement of the positron, how it is bent down and it went up. So according to the experimental evidence, the force on charge is directly proportional to magnitude of the charge. So if the magnitude of the charge is more, the force is more. Clearly notice the vectors. So here the purple vector represents the force magnitude in the presence of the magnetic field. Here the cross or the presence of the magnetic field. It means magnetic field is going inside the screen. We know that notation. Now in the second, the charge quantity is more, but that is moving perpendicular to the magnetic field, the green arrow mark velocity vector, and the magnitude of the force vector. So the force vector here is very big. So the force is directly proportional to charge. The force on the moving charge in a magnetic field. Here the charge should move. So it's directly proportional to magnetic. It's directly proportional to the magnitude of charge. Now, according to experimental evidence, the force on the moving charge is directly proportional to velocity. Here you can see two charges are moving with the different velocities. So the charge which is moving with less velocity, it experiences less force, and the charge which is moving with more velocity, it experiences more force. So this is also experimental evidence. So if the velocity is more, if the charge is moving very fast, then the force on the charge is more. Now finally, one more quantity, the force is depend. Here the force is directly proportional to the strength of the magnetic field. So here you can see the magnetic field is there, but it's not that much strong. You can see a noticeable gaps between the magnetic field. But here you can see the magnetic field strength is more. So the magnetic field strength is more, the magnitude of the force on the charge, that is also more. So the force effect on these three factors, one is the force directly proportional to magnitude of charge, and force is directly proportional to velocity of the charge, and force is directly proportional to strength of the magnetic field. So by combining this, we can write that force is directly proportional to QVB. Now here we can replace that proportionality symbol at a particular constant. The F is directly proportional to, F equal to some K times K. We can take that QV. K is K value equal to 1. Here one small change, if I can make it here, so that happens especially when it comes to the velocity component. So here we can say that velocity is a vector when it is moving, so it has two components, that is horizontal component and vertical component. If velocity is a vector, so this velocity vector is divided into two components, v cos theta and v sin theta, horizontal component and vertical component. Now we precisely says at here, the force is directly proportional to v sin theta, the vertical component of the velocity. How do we know this one? If you ask that question at here, so that is the reason why the charge particle is moving a spiral tracks. So if it is moving a spiral tracks, only one component is responsible. That we can understand from the centripetal force, like that. So the force here, one small change, okay, it's directly proportional to velocity, but that velocity component is v sin theta. So that is the noticeable component, and the force is directly proportional to magnetic field. So here the theta is the angle between V and B, because magnetic field is constant, but the velocity vector making an angle theta with the magnetic field. Now if together I can rewrite the same expression, Q B V sin theta. Here the Q charge is a scalar, so remove the proportional symbol, place a constant K, Q K times B V sin theta, and let's take the K value equal to 1, F equal to Q V B sin theta. Now for a simplification, if we can write that Q times, so the VB sin theta, we can write that V bar cross B bar, since velocity is a vector and B magnetic field also a vector. So the force, the magnitude of the force on a charge in a magnetic field, F equal to Q times V bar cross B bar. The cross product value gives us VB sin theta. Here the theta is angle between the velocity of the charge and the magnetic field. So this is the magnitude of the force of a moving charge in a magnetic field. Here we should more careful, because if any of the direction changes, then that corresponding direction gets changes. So we can conclude by giving a statement: a positive charge Q with a velocity V is perpendicular to the magnetic field, and the force proportionally equal to QVB. Here the V is the velocity vector and B is the magnetic field vector. To increase the force on the charge, any of these component is responsible, because charge, velocity and the magnetic field is 3 are proportional to the force. To increase the force, either you can increase the charge or velocity or the magnetic field. And very, very important, if the charge is not moving, there is no force acting on the charge. How it is? We can write that force F equal to Q B V sin theta. Here V is the V and B, theta is the angle between B and V. Sorry, I need to say theta is the angle between V and B. If there is no velocity, the charge is at rest, so there is no concept of the component V sin theta. This term equal to 0. So if that term goes to 0, the force on the charge goes to 0. It means I can re-say the statement: if charge is not moving in a magnetic field, on the charge there won't be any force. Yeah, but force will be greater. The force will be greater if the charge is moving perpendicular to the field. Perpendicular means the theta value equal to between the velocity vector of the charge and the magnetic field equal to 90 degree. You can substitute that in this value, F equal to Q B V sin theta. So here the theta value goes to F equal to Q B V sin 90 degree. Sin 90 degree value equal to 1, the force F equal to maximum Q B V. So if velocity equal to 0, then force equal to 0, or if velocity equal to 90 degrees making an angle with the magnetic field, then the force will be maximum. So like this we can find for any given value. Now you can guess what happens if theta equal to 180 degree. If theta equal to 180 degrees, that is the charged particle is moving either parallel or anti-parallel to the magnetic field. So sin 180 value, how much it is, and substitute that, how much value we will get it. Now to find the corresponding the direction, so before that, so the angle between the force and the magnetic field. Here the velocity vector is the very important, since the velocity vector is making an angle with the magnetic field. We need to take that particular component. So if theta changes from 0 to 90 degrees, you can see how the magnitude of the force changes. Now finally we can give the expression for force which is acting, the magnitude of the force which is acting on a charge in a uniform magnetic field, F equal to Q times V cross B, that equal to Q V B sin theta. So coming to the direction, so here this formula gives only to find the magnitude of magnetic field, but coming to the direction, so to give the direction, so I want to make you observe one more time the first slide which I played. Just observe the slide again at here, and how the charge is changing its direction. Again I am illustrating it here. Now the green arrow mark shows the direction of the charge. Here the charge is taken positive charge, and the magnetic field direction, that is directing from one side north to south and another side again from north to south. Now when the force interacts, when this charged particle moving in that magnetic field, so that is the force direction which is already represented at here. If you can notice, this purple arrow is the force direction, and if you can take the force direction in the other side, so here the force direction, now the force direction, here it is up, Do you notice the force direction this goes to downward direction, and here the force direction goes to upward direction. Now what could be the reason? So to understand the reason, what we need to do, we need to understand the magnetic field interaction with the velocity vector. Now if I draw magnetic field with this yellow vector, so this is the magnetic field. I will draw ahead at here. Yeah, this is the velocity vector and the magnetic field vector. Now the component of the velocity vector v sine theta is interacting with the magnetic field component. So these two interaction causes a force which is a downward direction. And when comes to at here to the another end, so the same velocity vector is same. I can represent that with the purple. So this is the velocity vector, and in this case the magnetic field vector direction has changed. Now the magnetic field vector is showing in this direction. Now the magnetic field vector and the velocity vector component, it's taking a component only, that is the v sine theta component. These two interaction causes the force upward at here. Means if there is any change in the direction, either the magnetic field direction or velocity direction, that causes change in the direction of the force. Now if it is moving at the 2 points in entirely different way, because the interaction of magnetic field at there with the velocity causes the change in the direction of force. Just like moving, just like sine wave, it happened like that. So here we will use one law or one rule. Right hand rule for the positive charge and left hand rule, that is Fleming's left hand rule, for the negative charge. So these two rules will help us to find the direction. Let's see the rules first. To find the direction of magnetic force, so by using a right hand rule, so Fleming's right hand rule. So with a flat right hand, point thumb in direction of velocity, fingers in the direction of magnetic field. Then the flat hand pushes the direction of force. Now extend this rule, if I can show on the screen because of the projection. Suppose if I take my right hand, for you it is left hand. And if I take my left hand, for you it is my right hand. So right now I am not using any hands to show you, that you follow which is showing on the screen itself. That could be very useful. Otherwise you will get confusion because of the projection on the screen, left to right, right to left. By using these laws for the left hand rule and for the right hand rule. So take your right hand, and in this right hand the curl of finger shows the magnetic field direction, and the thumb represents the velocity direction, and force on charge, and the force on charge represents the palm of the right hand. So this right hand rule we use for only for the positive charge or positron. And here you can see, if any of the component changes, the rest of the two components will changes. It's very tricky to apply the right hand rule. Always follow your own, okay, and apply it carefully. If any of the component is changed and the direction of the force gets changes, Now here I got the 6 different directions of the force. Always follow any one of the rule which makes you very easy to apply it, and try to keep your hand in such a direction in the given magnetic field. Then the rest of the two will follow it by itself. So try to apply the right hand rule very carefully, and what are the assigning to that particular fingers, that please don't get confused. The thumb represents the right hand velocity of the charged particle, and the curl of the fingers represents the magnetic field, and the palm represents the direction of the force. Or this is a very handy to remember. So because the velocity and magnetic field, they both are interacting. Suppose if it is a positive charge, the magnetic field exerts force on moving charges, and here to find the direction of magnetic force on moving charge, so that force is always perpendicular to the velocity and magnetic field plane. So the charge will move perpendicular to the velocity and the magnetic field plane. So because here the interaction is taking place between the velocity component and the magnetic field component. Okay. To define, so here I forgot to say one thing. Yeah, what happens for if it's a negative charge? If it's a positive charge, we use right hand rule. If it's a negative charge, just flip your hand. It means if electron is moving in a uniform magnetic field, then the same electrons also experience magnetic force, but the direction in that case is exactly opposite to the positive charge. So in this case, I suggest to use the same rule for electron by your left hand rule, which also known as Fleming's left hand rule. So left hand rule for negative charge and right hand rule for the positive charge. So after applying force direction rules for positive charge, Fleming's right hand rule, for the negative charge, left hand rule. So here we define very easily for the definition of magnetic field. So magnetic field intensity units, simple magnetic units, are nothing but Teslas. So how we define 1 Tesla or definition of a magnetic field? By using this formula, the force is directly proportional to BQV. It's only in terms of magnitude. Suppose if 1 Newton force is acting on a 1 coulomb of charge which is moving with a velocity 1 meter per second. So everything is 1, 1, 1. If 1 Newton force, otherwise from this formula I can write F equal to BQV sine theta. So this is a velocity component. Even the velocity component, if take the velocity V equal to 1 meter per second and the charge equal to 1 coulomb, which is a force acting on it 1 Newton. So we can define easily the magnitude of magnetic field. So here I can write that by rewriting formula B equal to F upon QV sine theta. If 1 Newton force acting on 1 coulomb of charge which is moving with 1 meter per second, then the intensity of the magnetic field there we can define as 1 Tesla. So this formula gives a very easy definition for magnetic field, F equal to BQV sin theta. So here you can get that units, 1 Tesla units. 1 Tesla is nothing but 1 Newton Coulomb per meter inverse. So how can I write 1 Tesla? 1 Tesla equal to, on numerator Newton is present, and the denominator C by S. If I can write charge per time, so this gives to me current. So current units are amperes. So the C by S quantity I can replace with A. So here you can replace that with ampere, and meters is already present. So 1 Tesla equal to Newton ampere inverse and meters inverse. 1 Tesla. Okay, so these are the very handy units to define magnetic field. So here how you define electric field, force per unit charge. So we define electric field equal to force per unit charge. It means Newton per Coulomb. So this is the definition for electric field. So I can encourage you, please remember like that magnetic field definition. B equal to force per unit charge along with the velocity. Here the velocity component equal to V sin theta. So this units becomes Newton amperes inverse and meters inverse, or the SI unit. So this is the easy way to define magnetic field by using the force charge velocity relation, and likely you try to get the dimensional formulas also. So many times we are neglecting the dimensional formulas. So here I can encourage you to get the dimensional formula for the magnetic field. Here easy to get it. Let us try to see the motion of the positive charge in a magnetic field in an animation. So here the magnetic field direction as shown, it is uniform magnetic field. Here an electron is moving perpendicular to the magnetic field. Just it is going to enter in the magnetic field. So if I draw the velocities vector direction, so the velocity vector showing along in this direction, and magnetic field vector is showing along in this direction. So they both are perpendicular. So velocity is perpendicular to the magnetic field. And here the velocity vector is having its component, that is horizontal component and vertical component. Now this velocity vector is making an angle theta at here. So the interaction of the velocity component V sin theta component and this with the magnetic field, that causes to move the electron here in a circular path in the magnetic field. Now when the electron enters, there is a resultant force which is acting on that charged particle electron. Now that causes the electrons to move a circular path in the uniform magnetic field. So the electrons moves in a circular path in a magnetic field. What happens if you bring a positive charge? Yeah, positive charge also same. Positive charge, but this time the direction is different. When positive charge is entering in a uniform magnetic field and its velocity direction with respect to the magnetic field, the component of the velocity component makes the charge move. Here the motion here you can see it's a spiral, not a circular. So this we can say it's a spiral motion, and this is also one of the reason, one of the natural phenomena that I will discuss later. It's a spiral. So the velocity perpendicular component is perpendicular to the magnetic field component, that causes the positive charge here to move in spiral. But when it comes to electron, so that electrons moves in a circular path. So here we saw two different types of motions for the two different charged particles. So let me play again. So the electrons are moving in circular path in a uniform magnetic field due to because of the interaction of the velocity component with the magnetic field. It moves a circular path, and when the charge becomes positive charge, if the polarity of the charge is changed positive, it is entering in the magnetic field. The interaction of the parallel component, here V sin theta we call as parallel component. So the interaction of the parallel component with the magnetic field vector, so that causes to move the positive charge in a spiral path. So this is all about, I need to discuss the force on a charged particle in a uniform magnetic field. I would like to show one of the real experimental demonstrations how the electrons take the circular path. Here this is the real experimental setup. Here you can see this is a vacuum chamber, a glass vacuum chamber. So in that, one small electron gun, it means just like laser, which releases the electrons, and these two will be acts like a uniform magnetic field. Just like we learned, a circular currents will be passes on this uniform toroids. So the magnetic field, uniform magnetic field will generates. Suppose if you release an electrons there, if we can notice carefully, now is playing with that. So here this is electron beam. It means electrons are just like moving a rays, which is known as electron beam. Electron beam. So this is generating electrons at here. We can see that since they are in vacuum, so they interact, the electrons path we can see it. Now if he is playing with that a magnet, here uniform magnetic field not applied, but is moving just a magnet. So how the magnetic field, so here the magnetic field is interacting. The magnetic field is interacting to the electrons and their path is disturbed. So this happens when non-uniform magnetic field is applied. For right moment, it's applied a non-uniform magnetic field. So that's why this natural magnet is close to the electron beam. Now if you take out this non-uniform magnetic field, now if you switch on the uniform magnetic field, which is generated by this coils, the circular coils will generate uniform magnetic field. Now the uniform magnetic field at the center, so the electron beam is interacting there. So let us try to see the path. So here you can see how the electron beam is bending. If we can increase the strength of the magnetic field is more. So it is something is very beautiful. Now the electron beam exactly became a circle. Now if you can decrease, again it become flat. Now I wish I would like to see that one more time. It's very beautiful to watch. The interaction of the magnetic field with the electrons moving, that causes the circular path at here. Okay, I hope the things are clear. So finally, I'll conclude by saying, if a charge is moving in a magnetic field, in a uniform magnetic field, so it experiences a force. That force causes a particular type of motion. If it is an electron, it moves in a circular path. If it is a positron, it moves in a spiral path. The magnitude of the force is given by the relation F equal to BQV sine theta. So apart of that, to find the direction for negative charges and for positive charges. For positive charges, we use the Fleming's right hand rule to get the direction of the force, and for negative charges we can use the same parameters but by using Fleming's left hand rule. Try to use it carefully when the right situation comes. Don't get confused and don't mess up with the positive charge and negative charge.